Thanks very much. Firstly, thanks to the organizers for this very beautiful event and organizing the talks, and thanks to Rilem for this recognition. It's really a quite honoring one. Also in knowing the previous awardees of this kind of medal. For those who know me, I'm very passionate about low carbon construction in terms of concrete materials and structures. And this is quite a frequent topic that I talk about. But in this occasion, I was thinking that it's best worthwhile to take you through a journey which I think is kind of very rewarding in terms of career, but also in terms of outputs. And it's a very interdisciplinary journey, that of improving the serviceability and sustainability of concrete materials and structures as a whole. So normally I don't like fast-paced presentation, but this one has to be one of them because you only get 25 minutes to cover so many, 10 plus years of experience. This is supposed to work, but it doesn't work. It doesn't matter. Switch into... Okay, now it does. Okay. So normally the vision should be that we design sustainable and resilient concrete materials and structures. This is the legacy that we have to leave for future generations to address the longevity issues and to address the sustainability issues that I will not go into the concrete CO2 problem because this was something that Karen covered already. So jumping straight into what we want out of the structures that we design and that we develop in terms of materials. And we want to have sustainable and resilient concrete materials and structures. And under this framework, the three key aspects is serviceability, durability, and sustainability. And all these include different characteristics. From a serviceability perspective, we're interested in functionality, aesthetics, understanding deformation characteristics, but also leak tightness, crack control, early age and long-term behavior, temperature time effects, creep and shrinkage, and so on. Then on the durability front, our materials and structures to exhibit good service life and understand the service life implications. We investigate resistance to deterioration mechanisms, controlling measures, and how to predict all those. And then sustainability front, there we delve into the world of supplementary cementitious materials and the science behind it, and other these are traditional, emerging, novel, and so on. And alternative techniques for producing cements, mix optimization, structural optimization, and the range of different strength grades of concrete that we can produce and utilize in our structures. So all of these elements are interconnected with each other. But for this case, I'd like us to focus more on the combination of serviceability and sustainability, which is always has been for me, at least in my career, a kind of combination of material science and structural engineering. And these are quite important aspects because they really define ultimately how long we can have designs for and how sustainable our designs are. But it cannot be viewed in isolation in terms of normally material scientists operate independently to structural engineers, which operate independently, even from a scientific background. But ultimately, these should be intertwined, and at least for my case, this has been an interdisciplinary journey since the beginning of my career in the field. And that journey started with me being a PhD and postdoc researcher in Queen's University Belfast under the supervision of Marius Suchas, and very much investigating the early age behavior of concrete with supplementary cementitious materials, slags, fly ashes, and so on. And that entailed analysis in terms of hydration, cracking risk, autogenous shrinkage, a lot of numerical simulation, and ultimately mitigation of thermal cracking in concrete structures. And back then, we were quite interested on how the temperature and time affects concrete with supplementary cementitious materials. Because in construction, normally supplementary cementitious materials were not very much included when it came into high-speed construction or fast-track construction because of some strengthening issues or because the understanding of how the strength develops was not well provided. So this was something that we were investigating, in this case, in terms of slags and fly ashes, and we were evaluating the temperature sensitivities of the mixes. And by temperature sensitivity, there is more kind of a scientific term of how we can express that. We express that normally as an activation energy, which is an indicator of the temperature sensitivity of a particular mix. We can see that GGBS, which is slag, is normally more temperature sensitive than ordinary concrete, while fly ash is less temperature sensitive. And that really affects the early age behavior overall, not just the strength, but overall of the cementitious materials that we're investigating. And also identifying and trying to understand further deleterious aspects of high early age temperature curing, such as the crossover effect, where there is a detrimental effect of the early age curing temperature, high early age curing temperature on long-term strengths, and how by using supplementary cementitious materials we can mitigate those and predict those more accurately with different models. And we've had a closer look on strength gains. And normally when you look at strength gain, you look into casting mortar specimens instead of concrete specimens because of logistical issues or even cost issues, because mortar specimens are smaller. But we found, for example, that there are some discrepancies between the strength development of mortar between concrete specimens, and particularly on the strength gain rate. For our case, when we're doing this kind of temperature time studies on strength gain, on strength development, the strength gain became more important, and you see why is that later. But also, we're doing these studies because we wanted to investigate the maturity models for predicting concrete strength initially. This was why the maturity functions were originally developed, but also maturity functions known as also equivalent age models have been used throughout codes and numerical analysis software to predict the properties of the concrete aside from strength for considering the temperature and time effects. So in principle, maturity is kind of a simple concept, is a product of temperature and time, and the principle says that regardless of the combination of temperature and time, two concretes having similar maturities should have same compressive strength. And this concept is included in ASTM standard, which also includes recommendations for mortar specimen testing. But in reality, there are different maturity models, and these were developed, several years ago. Some of them back in the 40s and 50s, and since then there hasn't been so much development apart from kind of a research boom in the 70s. So we said, okay, we have to review all these models and understand their deficiencies and how these could affect prediction reliability in terms of strength, but also in terms of other properties as well. So through a series of studies, particularly for concrete containing supplementary cementitious materials, we investigated different curing regimes, different non-isothermal conditions for concretes with SCMs. In particular, for example, this was taken from a mock-up study of including blocks, walls, and slabs, and we were able to develop this kind of modeling analysis with maturity function for predicting strength, and actually pointing to what the deficiencies are. And the deficiencies are important because they hinder the further application of this approach in understanding the evolution of concrete properties. So there are different models that could be applied in different concrete supplementary cementitious materials, but there is a kind of increased variability. And this work has been actually the foundation for some of the national guidance documents that are floating around the world. The most recent one is the one in Hong Kong on use of maturity method in concrete. But it was also the basis for us to look into further improvements of the maturity models. And that included the development of the modified Nersol method, which is an improved maturity function from predicting strength. It's quite a complicated method to go through in 1 year, in one presentation, but just now. But the concept is that normally people trying to understand how the strength develops in terms of cumulative strength development at 1, 3, 7, 28 days, and so on. But with this method, we found that it's more important to understand the rate of strength gain and find a way to transform that rate from a reference temperature, let's say the standard curing temperature of 20 degrees Celsius, to another curing temperature, while taking into account the crossover effects. So with this method, we were able to improve dramatically the predictions of early age and long-term strength, and can be extrapolated to other properties as well. So, okay, that's good in theory, but how did we demonstrate the application, and is this being demonstrated at the moment? This is a typical precast concrete factory where a slab or a wall rather is cast horizontally, and then is being lifted after achieving an adequate strength. But sometimes, because nobody really knows what the strength is in this kind of samples or specimens or elements, the strength can be below the lifting strength, and some kind of deficiencies can occur, and damaged specimens or damaged elements that are eventually being rejected are generated. So we are able to produce this kind of very well articulated prediction of concrete strength, and to optimize the curing regime for precast concrete, but also maximize the use of supplementary cementitious materials in precast concrete, which is known to be quite carbon intensive, mostly SEM1 used in precast concrete. So we were able to produce, with an optimized process, mixes with 50% slag, for example, for use in precast concrete, which was unprecedented. But also in kind of in situ high-rise construction. This is an example from a 200-meter tall tower in the city of London, where we employed this method to actually maximize the amount of SEMs in the concrete, ending up for the core walls with a 16 to 24 hours lifting strength, or that was a jumping formwork process. We were able to use 50% of slag in the summer and 25% in the winter, while it was traditionally zero, actually, straight Portland cement in these cases. But as part of these studies, we of course had to investigate hydration and setting of these supplementary cementitious materials, and developed custom-made adiabatic colorimeters that you're seeing on the left-hand side, and also isothermal colorimeter studies. And we generated very meaningful data in terms of the effect of temperature on the evolution of hydration heat of concrete cements with different supplementary cementitious materials, and really understanding, for example, slags that have been predominantly used in massive concrete structures to control the temperature evolution, what it means to have high curing temperature in terms of slag hydration. And we're seeing, for example, in very high replacement levels, the secondary reactions associated with slag are reinforced at very, very high temperatures. And equally on the efficiency of reducing the adiabatic temperature rise, which is relevant, resembles really a massive concrete structure. What is the actual efficiency of slag and GGBS in terms of reducing the temperature? Okay, we know it reduces the temperature, but also it reduces the tensile strain capacity. So in terms of controlling thermal cracking, there was a bit of debate at the time, and we were able to shed some light on that. So ultimately, we use this data to construct numerical models. For example, curing optimization of precast concrete elements in terms of what is the temperature regime that is required, and what is the maximum percentage of supplementary cementitious material that can be used without compromising the schedule of production, but also to construct thermomechanical analysis models for predicting thermal cracking in semi-massive and massive concrete structures, and also taking this further into autogenous shrinkage studies, and with different supplementary cementitious analysis. We employed restraining devices. This is the typical ring test, and with modeling, we investigated how efficient is slag actually in mitigating this type of cracking phenomena. I wanted to find that at certain high temperatures, the efficiency of slag might not be as high as anticipated in terms of reducing the cracking risk, because of some increases, for example, in autogenous shrinkage and the decreased tensile strain capacity. But towards the end of that part of the journey, two quite career-defining occurrences took place. One was my introduction to some members of the TC 238 on supplementary cementitious materials that the current Rilem president actually was chairing, and that was working on improving codified models from some of the members of this TC, And we particularly focused on the FIB models and how we can improve those, because these type of models for strengthening are used throughout the industry, but are not providing adequate provisions for supplementary cementitious materials such as slags and fly ashes and other ternary blends. So through this work, we were able to refine the models and produce a simplified approach to accounting for supplementary cementitious materials in concrete strength development, also considering temperature and time effects, which resulted in very, very, very good correlations between strength predictions and actual strengths. And it's actually a simple method that has been adopted quite widely. At least I've talked to some people that have been adopting it. But also was my introduction to TC 254 on cracking and massive concrete structures. And this was quite important. So this TC was led by Eduardo Feberin and Miguel Azenia. I think previously was also led by Professor Durant as well. So that was a big thing for us at the time, because we were looking into the thermocracking massive concrete structures, to the hydration studies and temperature time effects. And massive structures suffer from residual stresses due to early thermal variations. And this TC produced a very comprehensive Rilem state-of-the-art report that you can all look up, but produced also some quite important deliverables in terms of other outputs. For example, there is a big kind of dilemma out there in the industry as to when a structure is massive or not massive, because if it's being classified as massive, there could be implications with developing additional reports, thermal control plans. There could be liabilities involved, and so on. And for not massive structures, it's kind of more easy life. You don't have to worry about cracking and so on. But there was not an evidence-based approach that could predict this type of cracking effects as the one in this massive spillway somewhere that I shouldn't be saying where that is. So we developed, through an interdisciplinary study and evidence-based approach, a kind of a simplified manner to assess the massive concrete cracking risk. And by saying that, it's like the massive concrete, mainly it's a problem of volume. You got a big volume, but it's not just volume. It's about volume plus where heat can dissipate from, but also what type of binder is being used, the binder content, and the interplay between fresh and ambient temperatures. So around that time, because I developed this working relationship with the TC leads, I landed in University of Minho as a visiting fellow for a short period of time, and this was a really deep dive into testing for cracking, shrinkage, thermal creep, and creep effects. And we led into the analysis of what restraining devices can tell us about the early age and long-term behavior of concretes with and without supplementary cementitious materials. And there I had the pleasure of working with one of the pioneers of this landscape, Konstantin Kovler, another Rilem legend, and we developed these in-depth studies on very straining devices, but also on advanced numerical analysis for predicting the multiphasic phenomena associated with concrete hardening, and particularly employing multiphasic models to account for hydration, so thermochemical moisture transport and mechanical models to account for combinations of hydration, shrinkage, and creep and structural effects. And this was quite useful to elucidate some insights on whether shrinkage is relevant in massive concrete structures, or in some structures that have been shrinkage is being disregarded. For example, we found that the self-restraining effect due to moisture gradient can be quite significant. That cracking is initiated due to the self-restraining effect at surfaces of the concrete, which was previously disregarded. So sometimes when we go on sites, we still see this problem because you don't have properly accounted for it. But as importantly, as I moved into my current role in ARC, which is kind of a very quite big kind of player in cracking, serviceability, durability, very much into lower carbon concrete and novel binders, class enclaves policies, structural optimization, and other cementitious composites. It was quite important because during that time we initiated the technical committee on cracking early age or long-term cracking, TC287. And okay, previously we were looking into the massive concrete structures as being the main candidates for cracking risk, but then cracking is an everyday problem in concrete across different timescales. It happens. So this was from a major infrastructure project. It's part of a shaft wall. It was cracked, and this is another problem in a tunnel. So things happen. Engineers design for crack control, but this occurs. It's not something that occurs only in this type of high-profile infrastructure projects that are underground structures that nobody will ever look at. Walking around, I'm pretty sure you will see some evidence of yourself. And these are just us between the TC walking around in different cities, mapping cracks in stations, ports, maritime structures, walls, and pavements. So yes, it is a problem. It is a sustainability problem because you have to use reinforcement to control cracking. You have to repair cracking, so you use additional materials. And we all understand the millions that are being spent every year in terms of maintaining infrastructure. So under this committee, we worked into the multi-scale understanding of cracking, analyzed codified and unquantified approaches, multi-scale simulations, materials approaches for crack control, and now we're finalizing the book that is going to be published hopefully by the end of this year. And quite importantly, we delivered some other important aspects, such as recommendations for thermo-chemo-mechanical modeling in massive concrete structures. And to my best knowledge, still for the time being, this is the first and only Rilem recommendations document for numerical analysis specifically. So that was a quite big deliverable from the committee, but also analyze in depth the models that are being used globally for controlling cracks in concrete. And there's no surprise that we get all these kind of cracking problems in the world because for a given crack width, different provisions, different codes provide different recommendations for reinforcement. So which one is the correct one? And we are faced with a big problem because controlling crack widths is kind of very well related to the reinforcement quantity. If you want to control the crack width, you have to add more reinforcement. If you have more stringent, more onerous crack widths, you need to add more reinforcement. And it's not just Portland cement and structural concrete that is a carbon contributor, it's also reinforcement. So that's a combination of materials and structures there. And that led us to really revisiting some of the assumptions that we're making when we're imposing crack width limits. And through working with other Rilem members like Cameron and Rada, we mentioned previously that cracking is actually very well correlated with rebar quantity. But we've seen some problems with adding too much cracking for crack control. This is a problem in the pile that was constructed relatively recently with over-reinforcement because of crack control, and concrete couldn't flow, so the durability was compromised. So, we were going for good crack width control, but in the end, we ended up with compromised durability and sustainability of the element. And we have some other examples from cracking in some critical locations. This is the airport runway in Madeira. Some of the massive pillars are cracked. This is a friend, Dirk Schlicker, pointing at the crack, but the crack does not contain any corrosion products or not showing any corrosion products and has been there for 20 years. So that initiated an activity that is still ongoing in London, that we're kind of excavating basements, for example, to see if there are any corrosion problems, if there are any cracked concrete with corrosion products and so on. And at the moment, we haven't found any. So we're thinking there might be some ways to relax some of the limits when it comes to crack width control and save for reinforcement quantity, which is also contributing to embodied carbon. While I want to talk for many different initiatives and things that I have the pleasure and the privilege, I would say, to work on over the years till to date, I would probably close with the final initiative that was on calcine clays, particularly calcine London clay, which also resonates with the Technical Committee 282 on calcine clays. So as part of a mega project in the UK, two inboard tunnels are being constructed in the Greater London area, and that includes 24 kilometers of two inboard tunnels. means that there's a significant quantity of excavated material that was going to be generated. Now, the excavation started like 4 years ago or something like that. When we're calculating the amount of excavated material, back in the time, it was 2018, we calculate about 5 million cubic meters of excavated material was going to be generated, and most of it was going to be London clay. And it is London clay because it's being excavated now. And we knew from the previous mega infrastructure project in the same region that it's kind of a logistically expensive process, but also sustainability expensive, at the expense of sustainability, to transport that clay into landfills, as previously it was moved somewhere outside Greater London to construct this, to build this nature reserve. But of course that had emissions associated with it. So we were thinking, what can we do to improve that approach, to have a more circular manner in our approach? And this idea really originated during the coffee in one of our Arab offices, and we thought, okay, we'll bring this clay and calcine it as we get it out from the tunnel boring machine and reuse it in concrete. And at first it was like, what is this guy talking about? Does he understand how concrete works? Fortunately, I did. And this has evolved since then in a quite very, very promising innovation. So, you see, has made the news even. And here are some examples of that initial studies that we carried out in 2018, where we initiated the first part of that innovation. Here's a collection point of clay, and here are some collected samples from colleagues from the contractor, SES JV. So at that point, you know, we found out from initial studies that the clay was low grade, quite low grade, low kaolinite content, around 12 to 25%. So there was a concern on the suitability of the clay for producing calcined clay for using in concrete. And at the time, we're privileged enough to talk with Karen, and Karen even was invited to come over in our headquarters in London, and we talked about the potential of using this clay as a supplementary cementitious material in terms of calcined clay, and this was the start of it essentially, because we gained confidence on the potential performance of the material. So we carried out some initial tests on PFL. You can see this R3 testing here. We're on the low side of kaolinite content, really kind of 17-20%, which is not great, right? Nobody would tend to use this kind of clays at the time for this kind of application. And we were quite fortunate because the TC on calcined clays, chaired by Fernando Maturena and Manu Santaram, was also kicking off. So we tied this work together with the TC, and there was mutual benefit in terms of exchanging knowledge and experiences in the development of this low-grade calcined clay technology. So initially we thought, okay, based on the graph that Karen shared as well, we can produce reasonable strength concrete for us to target C2025, which is like, let's say 30 megapascals cube strength on site, targeting low-grade applications. And makes sense because 150,000 of cubic meters in concrete in the project were of this kind of strength. And we did the test in the PFL, the initial investigations in the EPFL laboratories with the help of Franco Zunino as well. And we saw that, okay, maybe it's not as bad as we were initially thinking. We can actually get structural level concrete strength with this kind of initial LC3 assessment. But also, we can investigate binary mixes. And why? Because we generate too much waste, clay, that has to be transported. And if we can use as much of it back in concrete, it will be beneficial from a logistical perspective. So yes, LC3 was a kind of the promising technology in terms of the synergistic effects of calcined clay and limestone, but the binary concept was we use as much of this waste clay as possible in concrete. So that kind of initial work revolutionized how people were treating calcined clays in terms of low-grade clays, and really sparked up, rejuvenated the interest in low-grade clays, I would say. Further work in collaboration with University of Leeds and Susan Bernal's team We looked into these binary blends, and we did a number of rounds of calcination and investigation. Here you can see the process from as-received clay all the way to the powder that was eventually used. This is a sample from the site. And even going up to 70%, you can see that we can produce 40 megapascal strength approximately, depending on the water-cement ratio, which is really pushing it to the limit. And that was really confirmed from site mixes that were conducted on, that were developed and tested on the laboratories of the contractor, which is SES JV. And we can see that still, for these are three different mixes. I think with 50% calcined clay, we can easily get into the structural concrete range, which is 40 to 60 megapascals. And many people complain about the workability and the workability retention of these mixes with calcined clay. Yes, it can be a problem, but with appropriate engineering and with appropriate use of admixtures, we can produce concretes with very, very good workability, which has been retained up to 2 hours in a very satisfactory level. So these are all from site. You can see some happy people there and some of our collaborators. And yeah, this has been an award also received in innovation. Ultimately, the ambition is to actually excavate the clay directly, collect the clay that's been excavated for the tunnel boring machine directly on a mobile processing facility consisting of different compartments and equipments where, from point one, we get the as-received clay all the way to equipment 29, which is the final ground product. I'm not sure how I'm doing in terms of time.
Yeah, should slowly.
Okay, I don't have any more slides. I don't have a conclusion. I just have a thank you slide. Thank you to Rilem for providing the inspiring framework to develop all these ideas further. And hopefully we'll continue to provide this framework for the generations to come. And thank you also to my collaborators, friends, and mentors, and all of those who have worked with me all these years, with whom I wouldn't be here. So I'm so in front of you. Thanks a lot.
Many thanks for your interesting presentation, and congratulations again for the prize. We have some time for the questions or suggestions. Anya, if you have a quick one to start, that you talked about early age cracking, and in some cases we observed that in order to achieve the durability parameters, there is a trend to increase or to speed up the strength development of concrete structures, so concrete. And I wanted to know your opinion about how this speed up, strength development or the increase in the early age strength development of concrete may affect the early age cracking behavior of the structures.
Yeah, thank you. That's a very pertinent question. I think normally people tend to believe that stronger concrete is better concrete, but it's not always the case. When we're talking about stronger concrete, we're talking about, particularly for the early age cracking argument, that stiffness is being generated more quickly, so stresses are being generated more quickly. Possibly, that could mean that the mix or the particular structural element could be more prone to cracking. So there's a fine balance in terms of understanding what the impact of the strength is, strength development, stiffness development, and ultimately how they all tie together in the analysis.
Thank you. Suggestions, questions, remarks? Yes, with microphone. Thank you.
Thank you, Fragkoulis, for this very nice presentation. One general aspect, trying to change the mentality of people towards sustainability. How can be in balance with the cost of this work, the final cost, of this mega project that you showed us, for example?
Yeah, that's kind of a $1 million question, dear Maria. I think coming up with ideas is not enough. Coming up with creative ideas helps, but coming up with cost-effective ideas is what really drives people in the industry, because they are those who are implementing these kind of innovations. So for our case, to